For some unknown reason, I went off and left my lapel mic, so I'm going to have to stay a little closer to the computer today so it gets my voice. But before we get started in on the stuff that we need to cover today, last time we talked about a little bit about oxidation and reduction in organic chemistry, and we started talking about ways in which we can make alcohols by reduction of ketones and aldehydes. So I'll just put in parentheses an R group there. For example, we can reduce these things and we can get either primary or secondary alcohols depending on the substitution. And what were the reagents that would do this? Sodium borohydride will work, right? So sodium borohydride. What else? LAH, lithium aluminum hydride, right? Either one of these would work just fine. There are some practical differences between the two. We know that we can take sodium borohydride and do the chemistry in water or alcohol, and it works just fine. We can't do that for lithium aluminum hydride. Why? Yeah, it reacts very violently with water and alcohols, creates hydrogen gas under high temperature, and that's just a recipe for an explosion. And that's, in fact, what you see happening. Okay. We can also reduce other functional groups that contain a carbonyl, right? So we can reduce carboxylic acids, and we can reduce esters. And here we are going to get primary alcohols. Let me put prime there. Right? And we'll get the alcohol that happened to be this one. What reagent would we need for that? LAH is the only one that you know of right now that will do this particular reduction. Right, so we need a stronger reducing agent to reduce carboxylic acids and esters to give the alcohols that we're after. So basically what you have to commit to memory, right, is what the reagents will do, and you need to commit to memory that you get primary alcohols for everything except ketones, right? Esters give you primary alcohols. Acids give you primary alcohols, aldehydes give you primary alcohols, but ketones will give you a secondary alcohol. So those are the kinds of things that we need to start thinking about. So we talked a little bit about the mechanism in terms of the reduction of an ester to give a primary alcohol. Remember, we're going to add a hydride that's going to go through the tetrahedral intermediate, but then that tetrahedral intermediate collapses and the alkoxide functions as a leaving group, which gives us an aldehyde intermediate, which reacts again with the hydride, and that's how we ultimately get the primary alcohol. So there's a little difference in the mechanism. You got an extra step, but that's the essential need of it. All right. So let's look at a few examples. So, and these are real-world examples where, again, most industries like to use sophomore-level organic chemistry because it works really well and it's fairly inexpensive. Starting with molecule A, what's the functional group that we're interested in here? It's a ketone, right? They do the reduction with sodium borohydride and methanol solvent. They use methanol because it'll dissolve this quite nicely. You get the secondary alcohol, which is an intermediate B, and then they take that and through a few steps actually make ibuprofen. Ibuprofen is highly sold all around. You know, this is Motrin and Advil and all the generic versions, but it's made using sophomore level organic chemistry. Okay, so it's very useful. This is a little different situation. So here we have a ketone reacting it with sodium borohydride in the presence of methanol. Notice we've also got an alkene. Sodium borohydride does nothing to the alkene. It's very selective for the ketone. So we don't reduce the alkene in this particular case. we get the alcohol, and then through a few extra steps, they make muscone, which is actually a perfume component if you like musky types of colognes and perfumes. It contains this molecule, which gives it that, and it is made synthetically. We don't actually kill little musks anymore to make this. Okay, so this is a perfume component. It actually contains one chiral center, but it's a fairly large molecule for what we've been talking about so far. But it is useful in the perfumery and cologne type making stuffs. All right, so that's reduction. So we know what our reducing agents are, but well, we need to talk a little bit about oxidation. So that's exactly the opposite of reduction. And we said that an organic molecule gets reduced when we add hydrogen to it. We make carbon-hydrogen bonds. And so we're going to oxidize it. What are we going to do? We are going to remove electrons in the form of hydrogen atoms. So we're going to remove hydrogen from the molecule. That's actually an oxidation, right? So we can actually oxidize alcohols and give us a variety of different carbonyl compounds. Basically, all we have to do, right, is remove one of these hydrogens and the hydrogen on the oxygen, and we can get a carbonyl-containing compound. Now, if you're talking about a primary alcohol, which you see there, you have to be very careful. You can get aldehydes, but you can also get carboxylic acids. And so there are different reagents to give an aldehyde, and there are different reagents that will give a carboxylic acid. So you'll have to know what those are, okay? So we can get aldehydes under certain conditions, or we can get carboxylic acids, okay? Secondary alcohols, regardless of what oxidizing agent you use, you're going to get a ketone because there is only one CH bond that can be removed. There's not two of them like we have up here. And so we can only do a single oxidation to give a ketone. Tertiary alcohols, there's no reaction. And why is that? Because we have no hydrogens on this carbon to oxidize, right? So tertiary alcohols are inert towards oxidation, for the most part. Secondary alcohols give us ketones, and primary alcohols can give us aldehydes or carboxylic acids. So those are the functional group transformations that we need to commit to memory in this regard, okay? Now, you need to know what kinds of reagents that we have access to do this type of chemistry, right? And it actually turns out we have a lot of different reagents that can do this type of chemistry. And we're not going to talk about a tenth of them, okay? The list is actually quite large. But what you will notice in most of the reagents that we hold undergraduate students responsible for, they all contain chromium, okay? So for example, chromium trioxide, sodium dichromate, potassium dichromate. These are all very strong oxidizing agents that can oxidize alcohols to either ketones or carboxylic acids, okay? So if you have a primary alcohol and you have chromium trioxide or sodium dichromate or potassium dichromate, it will oxidize that primary alcohol all the way to the carboxylic acid, okay? Notice that chromium is in the +6 oxidation state. That's going to be important for us as we talk about this a little bit. PCC, however, is a different chromium reagent. It's actually a salt that has a pyridinium cation. Okay, so it's a salt. The chromium is still in the +6 oxidation state. It is soluble in things like dichloromethane, but it is very selective. And so what it will do is actually oxidize a primary alcohol to an aldehyde, and it will stop there. If, and only if, there is no water present. Water is the key. Chromium trioxide, sodium dichromate, and potassium dichromate are always dissolved in water. And so they will take the primary alcohol and oxidize it all the way to the carboxylic acid. You take a primary alcohol, you place it in dichloromethane, and you use PCC, it will stop at the aldehyde stage. If you take PCC and you place it in water, it will do the same thing that chromium trioxide and the other reagents will do. It will oxidize all the way to the carboxylic acid. So these are just two reagents that you need to know about in terms of oxidizing an alcohol to a carbonyl containing component. So if we look at an example here, we have 1-propanol, PCC. In the absence of water, you get an aldehyde, propanal. The yields of these reactions are actually quite good, essentially quantitative. These are very easy reactions to run. Here we have the same alcohol, but now we're using a mixture of potassium dichromate, water, some sulfuric acid, and you end up getting this carboxylic acid. Again, a very clean reaction, essentially goes to completion. What you need to know is that when we have a chromium reagent in the presence of sulfuric acid and water, this has a name associated with it. We call it Jones reagent. So if you were to come down to my lab, we have a bottle that's just labeled Jones reagent. It contains a mixture of chromium trioxide, sulfuric acid, and water. It could have just as equally contained a mixture of potassium dichromate or sodium dichromate. Okay, but Jones reagent will take a primary alcohol and it will oxidize it to a carboxylic acid. Jones reagent will take a secondary alcohol and oxidize it to a ketone. Jones reagent will take a tertiary alcohol and do nothing with it. Okay? So we're going to have different reagents that we need to kind of commit to memory here. Now this turns out to have some valuable use. So, I don't know, I guess it was back in the 80s probably when there was a big push for, does everybody remember what MAD was, Mothers Against Drunk Driving? Something like that. So back in the 80s, there was a big push to minimize drinking and driving because it was kind of running rampant. And so if you were, a lot of bars in different places would actually hand out these breath scans so that their patrons, after they've had their fun, they could do a breath scan and see whether or not they could drive or not. It was an attempt to curb whether or not, or to curb the drunk driving situation that we were experiencing. And these breath scans actually contain basically Jones reagent. So you have a tube, you have a solid support, usually something like silica gel or silica beads, and they would impregnate on that Jones reagent. And Jones reagent, chromium salts are colored, and they're typically orange. Okay, so you have this orange color. So chromium, the chromium is in a +6 oxidation state, and it's kind of an orange color. And what you would do is you would breathe into this tube, and in your breath it contained vapor of ethanol. And ethanol is a primary alcohol, and the chromium would actually oxidize that into the carboxylic acid. Okay? But as the oxidation is occurring, the alcohol is getting oxidized. What's happening to the chromium? It's getting reduced. So chromium is going from the orange +6 oxidation state to the green +3 oxidation state. And it's an indicator of how much alcohol you had in your breath. And so you'd blow into this thing and you would see how far the green went. And you would be able to determine roughly what your blood alcohol content was. And if your blood alcohol content was too high, they wouldn't let you leave until the blood alcohol content was at a reasonable level. Okay? And so these were quick little tests that people could use to determine whether or not they were capable of driving. And so it was an alcohol detector, and you just kind of blew through this thing, and it worked. It contained potassium dichromate, kind of has this yellowish orange look to it, and then it would turn green. What's the problem with these types of devices?
There's no way it's that accurate.
It's actually fairly accurate. Now, it's not accurate enough to know exactly what your blood alcohol content is, but it is accurate enough to know you're inebriated. Okay? So it can kind of give you an idea there. So people were using these things, and then what were they doing with them? Throwing them away. They were just tossing them in the trash. What's it contain? Chromium. Is chromium good for the environment? Not at all, right? And so you had trying to solve one problem, but we created another problem. Fortunately, today we actually have these things that are electronic with electronic sensors, and so you don't have to use the chromium anymore. But it was a quick, dirty, easy way to determine whether or not somebody could drive or not. And so this is just a practical use for these types of reagents. Okay? Here's an example that I did in my lab. So this is what Jones reagent that we have in our bottle looks like. So I just took a little Petri dish, put a few milliliters of Jones reagent in it. And what you can see is, I would call that orange, right? And then I took some of our absolute ethanol, 200 proof. I took a pipette. I don't know how much of it was in there, maybe a quarter of a milliliter. Added it to the Jones reagent, and it turns green. So you can clearly see that you can understand what this chemistry is doing just by looking at it. The nice thing that my students like about Jones reagent is that you know exactly when the reaction is over. You know exactly when the reaction is over. So what they'll do is they'll typically take whatever alcohol they want to oxidize, they'll put it in a round bottom flask, and they'll take the Jones reagent and they'll put in a funnel that drips it in slowly, and they'll drop it in drop by drop. And as long as alcohol is present, right, the orange drop hits and it turns green and it falls to the bottom as a chromium precipitate. As soon as we've consumed all of the ethanol or whatever it is that we're oxidizing, that last drop will stay orange because there's nothing for it to oxidize. And once we get an orange solution, it's like a titration. We know that the reaction is over and we've done all the chemistry we need to do. This is almost instantaneous, so the reaction is done quite quickly. It's very clean. You basically dump stuff together, you get your product. So it works pretty well. So basically in this case we're taking ethanol and we're making what? What's that compound? It is a carboxylic acid. That's a functional group. But what is it? That's acetic acid. And so we also know by the oxidation of ethanol that it's occurring because we know acetic acid smells like vinegar, right? And so you go from something that smells like beer to something that smells like vinegar. You know quite easily that the reaction is over both by visual inspection and by smell. Okay. Now the oxidation of ethanol is interesting biologically. This is what happens when you enjoy a beverage, right? You have liver enzymes, alcohol dehydrogenase, and that alcohol dehydrogenase converts ethanol ultimately into acetic acid, or the acetate anion because of the pH of blood. But basically what the liver does is it takes the ethanol, it oxidizes it to acetaldehyde, which is an aldehyde. There's water around, obviously. That water facilitates the oxidation, the further oxidation of acetaldehyde to acetate. And that's the normal process for the metabolism of ethanol when you have a drink. Okay? If you drink too much, right, and you start to feel the funny feelings, right, what's happening? The acetaldehyde is actually building up in concentration faster than your body can metabolize it and further oxidize it to the acetate anion. Acetaldehyde is toxic. It reacts with a variety of functional groups. It dehydrates you. It is what is responsible for the hangover. Okay? So the acetaldehyde, that's the bad stuff. The acetic acid that you generate, not too bad. Okay? But the acetaldehyde is toxic. And if you're drinking slowly, right, you're just enjoying your drink, as soon as the acetaldehyde is generated, it gets further oxidized and it gets processed quite easily. But if you drink too much, binge drink, your acetaldehyde concentration goes up. It can't process it too fast enough, and you can actually, kill yourself. So you don't want to do that. However, methanol, wood alcohol, is toxic, right? But it's actually metabolized by the exact same enzyme in the liver. But the products are different. So if you happen to make a mistake, and I don't know how you would, but if you happen to make a mistake and drink methanol instead of ethanol, it gets oxidized to formaldehyde. And then that formaldehyde gets oxidized to formic acid. What do you know about formaldehyde? Dead bodies. And what do we use it for? To preserve tissue. Preserved tissue ain't alive, right? So if you're generating embalming fluid, if you drank methanol, what's it going to do to you? It's going to start preserving your tissues. It starts with the eyes, you go blind, and then a little bit beyond that, you die. Okay, and it actually kind of embalms you, if you will. You don't even really have to worry too much about getting to the formic acid stage. But the formic acid, not good for you either. That is what is responsible for ant bites, right? They're stinging you with formic acid. Okay, so many of you want to go on and be physicians. Many of you will actually have a situation occur when one night you're in an emergency room. They're going to bring in a kid who accidentally ingested methanol. It happens. Because methanol is actually quite common in houses. You use it as paint stripper, and you can go to Lowe's and buy it, and some kid gets curious for whatever reason and opens it up and takes a drink. How are you going to treat this kid? Well, you might pump the stomach, but it's not going to do much by the time they get there. It's already going to be in the system. You're going to give them a bunch of ethanol. That's exactly right. You're going to hook them up to an IV, and you're going to start an ethanol drip. You're going to get them drunk. And why is that?
So the alkyl dehydrogenase is more selective for ethanol over methanol, so it doesn't convert methanol to formaldehyde.
That's right. That's essentially right. So even though the enzyme processes both of them, you're going to give them so much ethanol that the enzyme is going to be working mostly on the ethanol, and the methanol is going to pass through the body unoxidized. Okay? And so organic chemistry at work here, right? You're doing Le Chatelier's principle, if you will, right? It is important that you understand this stuff. So oxidizing these alcohols can have medical uses as well. All right, so today we're going to get more into Chapter 12. We're going to start talking about some more organometallic compounds that can actually function as nucleophiles in the chemistry with carbonyl compounds. But before we do that, let's review a couple of problems. So here we have a molecule that is being converted. What's the functional group transformation that we're doing?
Alcohol to a ketone.
Alcohol to a ketone. Just a alcohol? We've got two alcohols. Are they primary, secondary, or tertiary? Secondary. And what are they being converted into? Ketones. What reagent does that for us? Which is that? B is the right answer. Okay? Now you could have easily eliminated A and D. Right? A is just a base. That's not an acid-base reaction. That's an oxidation. D is an acid. Again, not an acid-base reaction. So it can't be D. But you might come down to where it's A and C, or B and C. Obviously, B is the oxidizing agent. C is A. It's a reducing agent, lithium aluminum hydride. What other reagents could have been here for this particular reaction? Potassium. Well, no, that's the one there. Potassium dichromate. Sodium dichromate could have been there. What else could have been there? Chromium trioxide could have been there. What else could have been there? Actually, PCC will do this as well. Okay. Why would we not use PCC? PCC is a little more expensive than potassium dichromate, but it'll still do the chemistry. Okay. PCC will take a secondary alcohol to a ketone just like Jones reagents will. Okay. Just about any oxidizing agent would have done this for us. Okay. And so your book has other ones listed as well. You need to have those memorized also. How about here? What's the functional group transformation? Primary alcohol to an aldehyde. And I need what for that? An oxidizing agent. Which one will do that? D. And that is what reagent? That is PCC, right? So, the one that you can eliminate right off the bat is A. And why can we eliminate A? It's a reducing agent. We're doing an oxidation, so we know we can eliminate that. However, B, C, and D are all oxidants. They are all oxidants. But D is the only one that will selectively stop at the aldehyde stage. If you had used B, it would have given you what? A carboxylic acid. And if you'd used C, also a carboxylic acid, even though we've only used potassium permanganate for the formation of diols, right? And remember I told you that potassium permanganate only does that if it's kept cold, right? Are you starting to see maybe now why, if it warms up, other things can happen? Because once you get a diol, that's an alcohol. And if it warms up, that potassium permanganate will continue to react with that alcohol and oxidize it, right? So that's why we needed to avoid heat when we were making the diols from potassium permanganate in the addition of two OH groups across a carbon-carbon double bond. That's why we needed something like osmium tetroxide, because it doesn't do that. So potassium permanganate does. What about this transformation? What are we doing? Ketone to an alcohol. What kind of reaction is that? That's a reducing, that's a reduction, right? So can we eliminate anything based on that? We could eliminate B. It's a reducing agent, but why can we eliminate it? Technically, I could reduce the ketone with that. But it would also reduce what other functional group? The alkene, right? We know that hydrogen and palladium reacts with alkenes, and that remains unchanged. So I know we can eliminate it. We can also eliminate C, because C is sodium hydride. Sodium hydride does not behave like sodium borohydride or lithium aluminum hydride. Remember, sodium hydride is a base. It is not a nucleophilic source of hydride, interestingly enough, even though it is H-. It does not behave as a hydride reducing agent to react with a carbonyl. So that leaves A and D. Which one's the correct answer? A. That's right. We want to leave the ester alone, right? We're only reducing the ketone, and the sodium borohydride is the selective reducing agent. It will reduce aldehydes and ketones, but it leaves esters and carboxylic acids alone. If we had used D, what would have happened? That's right. We would have reduced the ketone, and we would have reduced the ester. Okay? And if that's what we wanted, that would have been the reagent that we would have needed to have picked. Okay? All right. So far we've been talking about hydride nucleophiles, and we've been talking about those nucleophiles coming from things like sodium borohydride and lithium aluminum hydride. And we can take those nucleophiles and we can add them to carbonyls, and we can get these tetrahedral intermediates, which ultimately give us alcohols. We are not limited to just hydride nucleophiles. We can use carbon nucleophiles as well. Carbon nucleophiles will react at the carbonyl carbon and form a new carbon-carbon bond. Instead of this being a carbon-hydrogen bond, we will generate a new carbon-carbon bond. And in doing so, we can ultimately get an alcohol. This is important for a couple of reasons. The most important of which is the fact that there are only about 5 or 6 ways to make carbon-carbon bonds. And this is one of them. How else have we made carbon-carbon bonds? How did we make carbon-carbon bonds on the last inverted lecture? Well, tosylate, in theory, could work, so I won't count you wrong there. But on the last inverted lecture, we used that for the Williamson ether synthesis, which made carbon-oxygen bonds. Remember we took an epoxide and we reacted it with an alkanide? One of these things, right? And that made a carbon-carbon bond, right? Because the carbon nucleophile attacked the epoxide. And did it attack, which carbon did it attack the epoxide? The most substituted or the least substituted?
least substitute?
Least substituted, and why?
Because it's not, the oxygen isn't protonated.
Because there's no acid around, right? Absolutely. So under acidic conditions, we attack the most substituted carbon, but under basic conditions with these types of nucleophiles, we're always going to attack the least substituted carbon of an epoxide. These reagents, okay, are all carbanions, and I put it in air quotes, okay? They behave as if the carbon has a formal negative charge. They are organometallic species. There are carbon metal bonds. When you have a carbon magnesium bond like this, we call that a Grignard reagent, after Victor Grignard. He won a Nobel Prize for this, actually. These are important reagents. They're very, very useful. You all will actually make a Grignard reagent in the lab and utilize it. We'll talk about those in a minute. Alkyl lithiums have a carbon lithium bond. They are organometallic reagents. They are stronger forms of Grignard reagents. We will not let you all work with alkyl lithiums. Alkyl lithiums are actually fun to work with if you know what you're doing, but they're also very dangerous. I can take a syringe full of what's called tert-butyl lithium, and I can squirt it out in the air, and it will spontaneously combust into a green flame. Grignard reagents do not do that, thankfully. So the bad news is, it's probably been 5 years ago now, there was a young lady at UCLA, I believe it was UCLA, who was working in the lab by herself. She was a postdoctoral associate, so she already had her PhD. She was working in lab by herself. She was working with a concentrated solution of one of the alkyl lithium reagents. I can't remember which one it was. I think it was tert-butyl lithium. And you have to work with these in air-free conditions and use syringes and needles and all kinds of stuff. And it turns out the plunger of the syringe came out, and like 100 milliliters of alkyl lithium squirted out onto her, and it spontaneously burst into flames, and she died. Okay? That does not happen with Grignard reagents. They are reactive, but they don't spontaneously burst into flame. So when you all are in lab, you're only going to be working with Grignard reagents. We're not going to allow you to work with alkyl lithiums. But the chemistry, what they do in terms of attacking a carbonyl, is essentially the same. Okay? Now these behave the way that they behave because the carbon metal bond is polar. Carbon, we know where it sits on the periodic table, and we know where these metals sit on the periodic table, right? We know that carbon is more electronegative than these metals, and so it pulls electrons in the bond to itself, giving the carbon a partial negative charge and giving the metal a partial positive charge. And so if you think about some of these organometallic reagents, if the metal is something like sodium or potassium, these are really ionic bonds. The carbon really has a formal negative charge, and the sodium or the potassium actually has a formal positive charge. Okay, so they're ionic. If you're talking about magnesium or lithium, these bonds are actually polar covalent. It's a true covalent bond, but the carbon has a significant partial negative charge to it. Okay? And if you're talking about other metals like lead, tin, or mercury, okay, these are actually covalent bonds. Okay? Even though there is a partial negative and a partial positive, the polarity is not quite as great as it is if it's magnesium or lithium. Okay? Have we talked about any of these reagents before? Actually, we have. Mercury, the oxymercuration-demercuration sequence, remember one of the products is an organomercurial species. And then we reduce that off with sodium borohydride to do the chemistry. But we have talked about mercury-containing organometallics. We haven't really talked about lead ones or tin. And we're going to focus today mostly on Grignard reagents and alkyl lithium. Okay. Preparing these reagents is actually quite easy, believe it or not, as long as you keep the reaction dry. Water will kill these reactions very, very easily. So for example, if you want to make an alkyl lithium reagent, you take some type of alkyl halide, either an alkyl iodide, an alkyl bromide, or an alkyl chloride. You react that with 2 equivalents of lithium metal in an inert solvent, and you'll get your alkyl lithium reagent plus lithium salt that falls out of solution. Okay? So you take the way that I've done this in the past is you take the alkyl halide, you put it in your solvent. Typically we cool this down to -30 or so because it does generate some heat. We put it under an inert gas, dry nitrogen or dry argon. We have to make sure it's dry. We don't want any moisture from the air. And then we take lithium metal and we chop it up into little squares and we drop it in slowly over time. And you'll see the reaction start to occur and you'll have this white lithium salt that forms at the bottom. And you've generated your alkyl lithium reagent. Notice fluorides can't be used. Alkyl fluorides do not do this type of chemistry. You're really limited to the chlorides, bromides, and iodides. The chemistry, again, is quite easy. Very easy to do in diethyl ether as long as you're going to use it immediately. So when I would generate these types of reagents, I would use diethyl ether and then I would go on and use it immediately. You can buy a lot of these alkyl lithium reagents from a company called Aldrich, and there's other companies that sell them as well, but you will never buy them as a solution in ether. And that's because the alkyl lithium reagent will react with ether slowly to actually decompose the ether into an alkene plus a lithium alkoxide. Can anybody explain to me why this reaction occurs? And in fact, if you leave it long enough, this will actually go completely to the right. What do you think the pKa is of an alkyl lithium reagent? 35? Why say 35? It's actually higher than 35. It's around 50. That's about as high as you can get. What's the pKa of an alcohol or the conjugate acid of an alkoxide? 16 to 20. So I'm going from a pKa of 50 to a pKa of, let's just say, 16. So where's the equilibrium going to lie? Does it lie to the stronger base or the weaker base? Weaker, right? And so this chemistry will actually occur slowly. Now, I can generate these in ether, and if I use them immediately, it's not a problem. It takes a few days for this reaction to occur. But if I want to make this and put it in the refrigerator and store it for use next week, this is a bad way to do it. And so usually when you buy these organolithium reagents, they come in something like hexane or pentane or decane solvent, just a pure hydrocarbon that doesn't have any oxygen atoms associated with it. Some of the easiest chemistry to do, actually, is to make these organometallic reagents like the alkyl lithiums. The Grignard reagents are a little more difficult to make and depend on your skill a little bit. These were discovered sometime around 1900, and Grignard again won a Nobel Prize in 1912 for this. These are reagents that are now over 100 years old, and we still use them all the time in organic chemistry. They are used to make the medicines that you all take. They are used to make the materials that you all use. They are very, very useful reagents. In theory, they are easy to make. You take an alkyl halide, you react it with magnesium metal. The magnesium metal simply inserts between the carbon and the halogen. We are not going to talk about that mechanism. It is a free radical mechanism and it is complex. All you need to know is that the magnesium inserts itself between the carbon and the halogen. Okay? It just simply inserts itself in between here and you have a carbon-magnesium bond and a magnesium-halogen bond. Okay? These are stable in ether because a Grignard reagent is not as basic as an alkyl lithium. In fact, a Grignard reagent, somewhere the pK is going to be somewhere around 35-ish, and that's why I was wondering, Anna, where you came up with 35. So substantially less basic than an alkyl lithium. Okay. Iodides react better than chloride, or bromides react better than chlorides. This reaction, when you do this in lab, is going to test your lab skills, because if your glassware has even a trace amount of water, this reaction won't work. Can anybody tell me why? The water will react. How? What's the pKa of the Grignard? What's the pKa of water? What happens if we generate a little Grignard? It'll react with the water. It's just an acid-base reaction then, right? And so it's kind of a cool reaction to watch. You start off with magnesium turnings. Magnesium is just a solid metal. It's in the ether. It's just sitting there stirring. It's kind of shiny. And as you add the alkyl halide, it looks like the magnesium is actually dissolving into solution, and the solution kind of turns a gray color. And you just watch for the disappearance of the magnesium metal, and you know when the reaction is over. So it's a pretty interesting reaction to watch, and you can end up with the Grignard reagent that then you can use to do the other chemistry. Okay. So let's focus on the Grignard reagents, noting that the alkyl lithiums are essentially the same. Again, we can make a Grignard reagent quite easily from magnesium and an alkyl halide. That then will react with a carbonyl-containing compound, let's say a ketone, and ultimately we will get a new carbon-carbon bond and an alcohol in the product. What is work up here? It is dumping these things over dilute acid. So you make the Grignard, you react the Grignard with your carbonyl compound. When the reaction's over, you typically dump it into ice with a little bit of acid and let that melt, and you get an alcohol. So if I take a ketone and I react it with a Grignard, what's my product? If I have a ketone and a Grignard, would it be a secondary alcohol? It would be a tertiary alcohol. Right, I've already got two carbon-carbon bonds to the carbonyl, and I'm making a third. So that's going to be a tertiary alcohol. So a Grignard plus an aldehyde makes a secondary alcohol. A Grignard plus a ketone makes a tertiary alcohol. Okay? The chemistry, the mechanism is quite simple. You take the sigma bond between the carbon and the magnesium, and that's where you start with your line, your arrow. You're going to push that pair of electrons to the carbon of the carbonyl, and you're going to break the weak pi bond. Okay? And you end up with a magnesium alkoxide salt. That's the intermediate. That's what happens when you add a Grignard. Okay? And then in the workup, this alkoxide simply reacts with the dilute acid to make the alcohol. Okay? You have to have that as two separate steps. On any kind of question I give you with a Grignard, if you would write the Grignard / H3O plus, that's wrong. Why is that wrong?
One than the other.
That's right. It's one and then the workup. You can't list them together. That would have to be counted wrong. Okay? The lithium reagents, exactly the same chemistry. Just push the arrows the same way and you end up forming the alcohol. Okay? Typically, we don't use lithium reagents for this, typically, because lithium reagents are so basic that they can react with other parts of the molecule. Grignards are the go-to, but sometimes you do need to use the lithium reagents. Okay? And we'll talk more about that as we move forward. So I want you, we've got a minute or two here. Fill in the boxes for me. How would we prepare? What do we need to prepare these reagents? What do we need to make the phenylmagnesium bromide? Pardon? Okay, so diethyl ether. And what else do we need? All right, so I need bromobenzene. And what else? And I need magnesium. So magnesium plus bromobenzene gives me the phenylmagnesium bromide. What do I need to make the methyl lithium? Methyl bromide. Now that's if I'm going to make it and use it quickly. How do I know I need methyl bromide? Why can't I use methyl iodide here? It is very reactive. That's true. But how do I know in this problem I can't use methyl iodide? Looking at the products. The lithium salt was lithium bromide, right? So that's how I know. Would it have worked to make the methyl lithium? Absolutely. But that's not what the problem asks. Okay? So I've got your inverted lectures from that you turned in on Wednesday. I'm going to rework these problems and post them. I've given everybody credit this time for this one because I didn't have time to grade it all. But I want you to go back and look at it, okay? That's your promise to me for getting the gift, right? All right.